Video 4, Rice and Advanced Lifecycle Optimization. My name is Tony McGuckin. I'm a senior software engineer with IBM in Ireland. I'm an XPages runtime subject matter expert and work on research and development of the server, client and mobile runtime, customer enablement, proof of concept development and technical pre-sales. I'm also involved with areas of user experience, performance and scalability, and system architecture. I'm a co-creator of the Global XPages workshops, an OpenNTF contributor, and sit on the IBM One UI Web and Mobile Adoption Workgroup. Further to this, I have co-authored 2 publications on XPages, the Mastering XPages book and the XPages Portable Command Guide book. Currently, you are watching Video 4 from the first series. Video 4 will teach you about 4 of the main characteristics of the XPages Request Processing Lifecycle. That is reliability, integrity, consistency, and efficiency. And we will also take a look at advanced lifecycle optimization within these 4 key areas. Video 4 begins by briefly revisiting some of the information that we have learned from Video 2 in and around understanding an XPages request and the XPages Request Processing Lifecycle. Then we will learn about 4 of the main characteristics of the XPages Request Processing Lifecycle before we then take a look at worked examples taken from the lifecycle.nsf application in the areas of reliability, integrity, consistency, and efficiency. Finally, we will take a look at a case study where we will use the knowledge learned from videos 2, 3, and 4 to optimize some common day use cases within the Greenwell Helpdesk application. Video 2 introduced us to the XPages Request Processing Lifecycle. In that video, we learned all about how an XPages request is processed within the XPages runtime. Please refer to Video 2 for a full introduction if you have not already watched it. The main point that Video 2 conveys is the fact that for every given XPages request and response, there is a governing XPages Request Processing Lifecycle that is central to the processing of that request, and ultimately will determine how much memory and CPU is used in order to process a request. All of the other factor areas that will have an influence over the speed of a request are hinged externally to this XPages Request Processing Lifecycle, therefore making the XPages Request Processing Lifecycle the center of gravity for every XPages request. In Video 2, we learned about the XPages Request Processing Lifecycle in some detail. Some of the key points that were addressed within Video 2 are the fact that the XPages Request Processing Lifecycle is most typically executed for HTTP GET and POST type requests. We also learned that there are 6 key phases. And for a GET type request, phases 1 and or 6 are executed, versus a POST type request where phases 1 through 6 can be executed with some variance depending on the requirements of the request. We also learned in Video 2 that phases 1 and 6 are recognized as system level phases and are executed for most HTTP GET and POST requests, where there is a difference for an AJAX GET versus a standard GET request. We also learned that phases 2, 3, 4, and 5, that is the apply request values, process validations, update model values, and invoke application phases, are known as application level phases and are executed for HTTP POST type requests. We also learned that there are 4 event pseudophases that are executed for each of the application level phases and are used to determine whether to proceed with execution of the lifecycle based on the previous outcome of processing within the last phase. And one very important aspect that has been alluded to within Video 2 is the fact that usage of the application level phases can be optimized per request requirements in order to reduce the amount of CPU and memory that is used within the XPages runtime. And we will now concentrate on this particular aspect of the XPages Request Processing Lifecycle here within video 4. The XPages Request Processing Lifecycle can be viewed upon as having 4 main characteristics, categorized as follows. Firstly, reliability. Events and actions are governed by the lifecycle phases, and this is provided by the predefined order of execution that we see within the XPages Request Processing Lifecycle. If we think about such things as events and actions, and event listeners, action listeners, value change listeners, phase listeners, and so forth, there are lots of mechanisms built into the XPages Request Processing Lifecycle which will predefine the order of execution and therefore provides us with absolute reliability. Secondly, integrity. Input values are protected by input rules provided by conversion and validation mechanisms. Data integrity is paramount at all times. The system should not be compromised by either a change within the client-side UI or the server-side UI that is not reflected in either context. Thirdly, consistency. Components and objects can have different lives during request execution. This is provided by scoping and persistence mechanisms within the XPages runtime. This ensures that for any given object or component that it will exist if and when it is expected to do so. These mechanisms also shield data from concurrent access and ensure that the data and the objects are efficiently managed within the stateful web application architecture. Finally, efficiency. Request execution can be broadened or narrowed. This is provided by magnitude mechanisms to control the impact of any given request. Given that you're working in a stateless HTTP environment against a stateful web application framework, a request is then being issued against the state machine, aka your Domino server. And as we have come to learn in videos 2 and 3, the request is then being executed against a component tree. So in terms of providing the most efficiency, this is where you as the XPages developer can have the most influence over the XPages request processing lifecycle, in that you can program your application to influence and affect the application phases and therefore broaden or narrow the impact or the cost of any given XPages request in order to minimize the amount of CPU and memory utilization on your Domino server or XPages Notes client. In order for something to be reliable, it should expose a repeatable and dependable process. And that's exactly what we see with the XPages request processing lifecycle. In that when it receives a request, it handles that request and executes the application logic in a predefined and repeatable order that we as XPages developers can always depend upon. In this next example, I have opened up the test view events XPage from the lifecycle.nsf application. And as you can see here, the XPage contains a number of different buttons. But what I want to draw your attention to is the fact that the page uses a set of view level events, as we can see here. Here we are making use of the before page load, after page load, after restore view, before render response, and after render response view level events. And you may have always wondered where exactly these events get invoked during the processing of a request. So that's where we can now use the lifecycle.nsf application along with our phase listener to introspect the lifecycle processing and to also then see where these events are getting executed. Now also note the fact that for each of these events, there is a simple println statement being emitted to the server console or your OSGI client console. So for example, taking a look here at the before page load event, as you can see here, there's nothing more than a simple println statement telling us exactly which event has been triggered, and the same format has been used for the other view level events. The other thing that I want to draw your attention to within this example is that for each of the buttons, they are configured differently to either execute a full submit or a partial refresh. So for example, if we take a look here at this first button, which is a full submit, as we can see here, the event handler is set up with its server options set to full update. And again, there's nothing more than a simple println statement being emitted to the server console or OSGI client console. And again, if we take a look then at the second example, the second button, which tells us it's a partial refresh submit, again, a simple println statement, but the server options this time are set for partial update, as we can see here. And in the third instance, if we take a look at partial refresh submit immediate, as we can see here, we have a very similar button to the second one. Again, we have a println statement, and the server options are set for partial update. But furthermore, we can see here that the checkbox for do not validate or update data has been checked. So I have now brought up my browser and Domino Server Console, and on the index page of the lifecycle.nsf application, I am proceeding to turn on debug mode. And again, you should refer to video 3 if you're not familiar with the introduction to the lifecycle.nsf application. In video 3, you will find a full introduction that explains debug mode and how we use a phase listener and so forth to capture live lifecycle introspection information, as we can see here on my Domino Server Console. So moving on from that, if I then open up the test view events XPage that we were looking at inside Designer, we can immediately see that on the Domino Server Console, the page has been loaded. So if we take a look then at the information on the Domino Server Console, we can see that our before page load and after page load events have been triggered during the page load process. And given that it is a full GET request, the restore view phase is not triggered. Instead, the page is loaded and the page load time bindings and before and after page load events are triggered. And subsequently then the render response phase triggers the before render response and after render response events accordingly. And just to draw a comparison between the full GET versus an AJAX GET, if I then proceed to click on this fourth button, AJAX GET Submit, we can see that in this case, the before page load and after page load events are not being triggered. We have already loaded the component tree, and in this instance, it is an AJAX GET request. And hence, in this case, we can see that the restore view phase is triggered, and then the after restore view event is triggered. And then again, we come into the render response phase, where our before render response and after render response view level events are triggered. We can also then click on the partial refresh submit button. And in this instance, we are performing a partial refresh submit using HTTP post. So in this case, we're interacting with the XPages Request Processing Lifecycle using a post request. And this in turn causes the invocation of all 6 phases of the lifecycle. But once again, what is important to note is the order of the page level events. Again, we can see that the after restore view event is triggered during the restore view phase. And subsequently, when we come into the render response phase, we can see the before render response and after render response page level events being triggered. And if we tick the third button in our page, the one that is set to not use validation or update data. If I click on partial refresh submit, and in this instance, we can see that only 3 of the lifecycle phases are being invoked simply because the immediate property stops the runtime from processing any validations or updating the backend data model. But what's interesting to note here is the fact that the event handler code is now brought forward and executed inside the apply request values phase, which is slightly different than the previous request where we were not using immediate equals true. And if we compare both of those invocations, we can see in the previous example, when we clicked on partial refresh submit, the event handler, which is emitting the simple println statement, was invoked during the invoke application phase. Comparing that to the partial refresh submit, which uses immediate equals true, as explained, we can see that the event handler has been brought forward into the apply request values phase. In summary, the point of this particular example is to demonstrate the predefined order of the lifecycle phases being invoked and processed versus the view level events that we see on the XPage itself and the event handlers and so forth, to simply demonstrate how those all fit together and are executed in a repeatable and dependable process. In order to provide data integrity, the XPages runtime provides a number of different conversion and validation mechanisms which you as the XPages developer can leverage. For example, here within the lifecycle.nsf application, I have already opened up the test process validations phase XPage. This XPage contains 4 input fields, as we can see here inside the WYSIWYG editor. But more interesting is to switch over to the XSP source markup. And if I just scroll to the top of the page and work my way down through the examples, what we can see are 4 different examples of using combinations of validators and converters in order to achieve data integrity. So for the first input text, what we can see is that it defines a required clause in that it has a required validator. Furthermore, it then has a custom converter using server-side JavaScript. And within this custom converter, we are declaring the business logic that we require. Now, one interesting thing to note is that here we can see use made of this value variable. And what I should say is that this is an implicit variable which represents the submitted value. So, in essence, this could in actual fact be replaced by this same fragment of server-side JavaScript, and we would equally as well get the same value as represented by the value variable. Furthermore, we can see how the server-side JavaScript custom converter also declares a getAsObject versus a getAsString implementation. This is important for converters in that when you are posting the page back to the server, the incoming value or the submitted value must be then converted into an object representation. So that's where your business logic, in this case within the getAsObject method, will take care of converting the incoming value into that expected object representation. Versus when the page is being rendered, during the render response phase, the getAsString method will be invoked. And in this case, the converter must take care of converting the object representation back to a string representation, which will then be used within the emitted HTML markup. Furthermore, if I scroll down the page, I can see a different implementation of a validator. Here we have server-side JavaScript representing our business logic for this particular validator. And again, in this case, what we're doing is using the submitted value, which again is used during the process validations phase. So we are dealing with the submitted value in order to check if the length of this particular value is greater than 6, and if so, the validator itself will create an error and stack that error onto the error messages queue. As we can see here within this fragment of server-side JavaScript. In addition, what we can see happening here with this particular input field is that we are using a converter which has been pre-registered with the XPages runtime by way of the faces config for this application. So for example, here we can see that the converter ID is foo converter. So if I were to open up the faces config file for this application, we can see here on lines 25 through 28 that there is a declaration for the foo converter, and this declaration points at a converter class, as we can see here. Again, if I were to open up that foo converter, it's nothing more than a simple Java file which implements the Java XFaces converter interface. That interface declares that any implementers should provide a getAsObject or getAsString method implementations, as we can see here. So effectively here what we can see is that the same business logic that was encapsulated within our server-side JavaScript is now ported and converted into Java and represented here within our custom Java converter. As we can see here, the getAsObject versus the same getAsString implementations. And looking at the third input field, here we can see on line 77 that it declares a validator using the validator property, and it appears to be using a backing bean whereby the binding directly uses a validate method on the backing bean. So if we were to look at the var bean implementation within the application, we can see here that this var bean includes a validate method as seen here on line 47. And again, the business logic for this validator is represented using Java, as we can see here. And again, given that we're working inside the process validations phase, we have access to the special submitted value, which is then used within the business logic of the validator. And if we now just come back to the XPage itself and look at the declaration for the fourth input text field here on line 82, we can see that it, in this case, uses a pre-registered validator, similar to the way that we used the pre-registered converter in the second input field. So in this case, again, we can look at the faces config file, and indeed we can see here on lines 29 through 32 that there is a custom validator registered for foo validator, pointing at a special validator class. So once again, if we choose to open up the foo validator, we can indeed see that the business logic for this validator is encapsulated within this validate method here on line 21. In summary, we can now see that we have an XPage showing different permutations or combinations of using custom validators and converters in order to ensure data integrity for this particular XPage. I have now brought up my browser and Domino Server console and switched over into debug mode. And if I now try to submit the test process validations phase XPage, I can immediately see that the required validators on the first two input fields are triggered. So as we can see inside the user interface, each of the input controls have their corresponding error message controls showing their required value messages. And in addition, we can see that both of those required messages appear within the error messages control at the bottom of the page. Furthermore, given that we have posted the page by clicking on the submit button, we can see that the request caused an invocation of the request processing lifecycle, which in turn restored the view, applied the request values, and then inside the process validations phase, the validators have failed in this case. So the required validators in both cases have failed, causing a direct failover into the render response phase, which then conveys to the end user the error message strings that we can see inside the user interface. So if we were to now provide some input values into the edit fields and again submit, in this case we can now see the converters are being triggered. So in both of these cases we can see that we have, for the first input field, we have the custom converter that uses the server-side JavaScript implementation versus the second input field, which uses the pre-registered Java converter that uses essentially the same business logic. And as an end user, I am oblivious to the back-end implementation of that converter. I essentially see the same conversion message here within the user interface. But for you as the XPages developer, you have the choice of either providing the business logic as an inline converter using server-side JavaScript, or as a reusable Java artifact that you can pre-register with the application, or indeed share across several applications per your requirements. So if we now provide values that would satisfy the constraints of the converters and so forth, we can now submit. And in this case, we can see that we have successfully submitted the page. And in this case, there is a complete invocation of the lifecycle in that we have 6 phases being invoked, which in turn demonstrates that the validators and converters attached to this particular X page provide data integrity. In order to provide consistency, the XPages Request Processing Lifecycle provides mechanisms which ensure proper scoping and persistence of objects within the XPages runtime. This ensures that there is a degree of order brought amongst the objects that exist within any given request context, and provides a foundational framework whereby the runtime itself can ensure proper memory management of the JVM heap space. So in our next example, we will take a look at the test simple lifecycle X page in order to gain an understanding of the consistency characteristic. Firstly, let me switch over to the XSP markup of the actual X page itself. And in this case, we can see that there is an input text field, 2 buttons and 2 labels included within the X page. The interesting thing to note is the fact that there is a managed bean binding on the input text, as we can see here. The input text value is set to simplebean.value. Also note the fact that the first button has an event handler which will submit the page and is using immediate false save equals true. So there will be a post request sent through to the XPages runtime. Also then note the presence of the bindings on the 2 label fields, as we can see here on lines 18 and 21. On line 18, this label again is bound to the simplebean value. And then we have a different example using JavaScript binding, whereby we call upon the simplebean getValue method. So 2 examples, one using expression language versus server-side JavaScript, that will both return the value property from the simplebean. Furthermore, let's take a look at the faces config for the application. And here we can see that the declaration for the managed bean on line 15 through 19 has set the managed bean scope as none in this case. And if we take a look at the managed bean implementation within the application, here I can find the simplebean. And here we can see that it's nothing more than a simple Pojo class that contains a constructor method, a finalizer method, and getter and setter methods for the value property. So let's now go back to our browser and Domino console and open up the simple lifecycle example. So first off, we can see that the simple bean has been constructed multiple times during the creation of the component tree for this particular request. Here we can see multiple invocations of the constructor, and also we can see that for each of the elements, that is the edit box and the two labels, that there are calls upon the getValue method of the simple bean, which in this case are returning null, simply because there is no predefined default value. Now let's proceed to input a value into the edit box and click on Save. And in this instance, what we are doing is submitting the page using a post request that in turn invokes our event handler. And as we can see here, the request has come in and in turn restored the view and then proceeded through each of the subsequent lifecycle phases. But what's very interesting and very worrying to note is the fact that we have multiple invocations of the simple bean constructor, and indeed here we also have the finalizer being invoked and so forth. So there does appear to be chaos amongst the higher level order of the processing of the lifecycle phases. So this is indeed not very consistent. And we can also note the fact that our incoming value for hello folks in that particular case is set on the simple bean value, as we can see here, during the update model values phase, but subsequently has been lost by the time we get to the render response phase. So all in, here we have an example of an object which is not being constrained properly within the XPages Request Processing Lifecycle. So if we now return to Domino Designer and make a couple of small changes to the application, we will then be able to demonstrate how we can constrain our custom object and make it work efficiently within the mechanisms of the request processing lifecycle. So first off, here within the Spaces config file, I changed the bean scope from none to view, as we can see here. And over inside the bean itself, what I'm doing here is changing the bean to implement the serializable interface. This in turn allows the bean to be managed by the managed bean container in order to ensure that it is persisted and scoped consistently. Let's now go back to the browser to test the changes that have been made. So once again, I put my browser just above my Domino console so we can see the output. And I just refresh the application to pick up the latest design changes. And now we can reopen our simple lifecycle XPage. So we can see right away that the changes that have been made have had an impact on the behavior of the application. In particular, here we can see that the simple bean is now only constructed once during the render response phase, as I requested the XPage. Also note the fact that the getValue methods are being called again. That is once for the edit box, once for each of the computed fields that at the moment don't have any values. So let's now proceed to input a value again into the edit box and click on Save. And in this case, here we can see that the request did indeed invoke all phases of the lifecycle. So here we clicked on the Save button, which started the request, which in turn then restored the view, applied the request values, executed process validations, updated the model values, and proceeded to invoke the application before finally rendering the response. But this time, note the difference in the behavior of the application. Notice how we now have a consistent and very efficient management of the simple bean object in line with the order of the processing of the lifecycle phases. Given that we have already requested the XPage in the initial GET request, which constructed the simple bean, we are now posting back against the same component tree. So in this case, the simple bean has already been constructed or instantiated, hence we do not see any initialization or construction of any simple bean instances within this particular request. What we do see is use now made of the get value versus set value methods on the simple bean. So for example, here inside the update model values phase, we see the incoming value that we supplied, hello folks, which now subsequently is persisted and survives subsequent execution of the invoke application phase and is readily available now inside the render response phase. And again, given that we have three elements that have a binding to the simple bean value, here we can see those three elements now obtaining the correct value, as we can see here. So the greatest benefit here in this particular example is that we now have a consistent execution of this particular XPage. The objects that reside within this particular XPage are now consistently scoped and persisted and managed within the JVM heap space, whilst the request processing lifecycle executes over this particular component tree. The XPages runtime provides you as a developer with many different settings and performance and scalability related features in order to ensure that you can create and deploy highly performant and robust applications. But in this last section of video 4 from Series 1, I want to explore some of the lower level intricacies of working with the XPages Request Processing Lifecycle in order to ensure that you can embellish the characteristic of efficiency well and consistently within your XPages applications. Almost every control within the XPages runtime supports the loaded and rendered properties. These are two properties which determine whether a control will be present within the component tree versus visible on the actual rendered HTML page. And it is important to understand the difference here because of the effect and the cost that this has on the component tree, memory and CPU usage when creating and subsequently processing any given component tree. The rendered property is evaluated on every request and more importantly will be evaluated in up to 4 out of 6 lifecycle phases for a post request. The loaded property, on the other hand, will be evaluated once per control tree, but not on each request. That is to say, if you have requested a given XPage, the loaded properties will be evaluated once during the restore view and page load processes. Any subsequent interaction with that same page during your session will not cause a re-evaluation of those loaded properties. If, however, you do navigate away from that current page and should then come back to that same XPage, there will of course be a re-evaluation of the loaded properties, given that a new component tree will be reconstructed for that XPage. Given these technicalities of rendered versus loaded, rendered is therefore more flexible in that you can develop the XPage with computed rendered properties that will be re-evaluated for every interaction upon that XPage, such as partial refreshes and so forth. Whereas, on the other hand, the loaded property will only be evaluated once as the page is loaded and subsequently not re-evaluated thereafter, such as any partial refreshes that are posted back against the XPage will not cause a re-evaluation of the loaded properties. The upshot here, of course, is that the loaded property is seemingly more performant in this case. However, the loaded property is not always a viable solution, or indeed not always possible, depending on the type of use case. As I just alluded to, particularly with partial refreshes, you will find that the loaded property will not be reevaluated within the partial refresh target area, for example. This can be quite restrictive in terms of creating a truly dynamic experience whereby you may want to show or hide certain parts of an XPage during that partial refresh request. Furthermore, things like view entries aren't available during the loaded process. So as the loaded property is being evaluated, such things as view entries and other types of application level data may not be available during the create view process. These same rules apply for the load time versus runtime computed value expressions. So as an XPages developer, you will be familiar with the $ versus hash prefix for computed expressions. The $ denotes a load time computed value expression versus the hash, which denotes a runtime computed expression. And finally, the same rules also apply within the before page load versus the before render response events that are available at the XPage view level itself. Let's now take a look at a couple of examples whereby we can analyze the effects of using rendered versus loaded properties. So inside Designer here, what I'm going to do is create a new XPage simply to demonstrate loaded versus rendered. Let's just drop on an edit box and a button onto this XPage. In the first case, on the edit box, here we can see the visible property exposed on the properties panel for the edit box. This visible checkbox actually maps to the rendered property. So for example, if I were to look at the source markup for the edit box, implicitly by default, rendered is always true for every control that supports the rendered property. But if I were to uncheck the checkbox, as you can see here, it now writes rendered false into the tag markup. And this is actually a very commonly used property whereby developers are creating computed rendered expressions in order to control the visibility of controls within their XPage. On the other hand, let's take a look at the all properties for the input text as well. And in amongst the different properties that are available, under the Basics tab, what we can see is that we do also have the loaded property exposed. Currently, we have set rendered as false, and here we also have the loaded property. And again, as described earlier, almost every control within the XPages runtime supports these two properties. And just to reconfirm the point again, the implicit default is true for both properties. In the interest of demonstrating loaded versus rendered, for this particular example, let's take the button that we have on the page and set its loaded property to false. So as you can see here, I have set false on the loaded property, and on the button it is written in loaded equals false. So let's now just save our new XPage. And within Designer, because of the translation, interpretation, and compilation process that happens within Designer to create the actual .class file representing this XPage, we can, of course, look at the corresponding test.java page, as we see here, that has been created representing our test XPage. So let's just go ahead and open up test.java. So this is the Java interpretation of your XSP markup that is generated within Designer. And if we look down through the Java code, what we can see is that this Java code will create the component tree as such for this XPage. But in doing so, it creates the child controls within the page itself. So for example, in the XSP markup, we do have a view root tag we have the input text control and the button control. But notice how that each of those method calls do create the corresponding componentry object classes. And in the case of our input text, where we set rendered equals false, Designer has created the corresponding Java markup to call on set rendered false in this case. But more interestingly, look at the effect of setting loaded on the button. Loaded will return null for this particular button. So this implies that the button control itself will absolutely not exist within the component tree versus the input text, which will, of course, instantiate an input text object, but simply not render it back to the requesting client or browser. This, of course, also implies then that the input text exists within the component tree, consumes an amount of memory, will incur CPU processing cost as the page is processed, versus the button, which simply does not exist, given that loaded has been set to false. Furthermore, if we take a look at that particular X page that we've just created, here within the resultant HTML markup, we can see that neither the button or the input text exist within the generated HTML markup. And if we also take a look at the server-side component tree by using the XPages toolbox, here if I create a full session XML dump, what I can do is open up that generated XML file, and we will see the structure of that particular X page. So for example, here within the XML markup, I can see that for that particular X page, here we have the representative XML for the structure. We have the view root. The view root has a child, which is a script collector, which then has the form, which is the view tag. And then we have the input text control. So this is proof that the XSP input text does exist inside the component tree on the server side, versus what we have seen in the generated HTML is that it doesn't display within the web page itself. Furthermore, as you can see here, there is no existence of the button control. So the button simply has not been loaded into the component tree in this case, given the generated.java file and compiled.class file that we have seen back inside Designer. So let's now just go back to Designer, and if we make a small change within the XSP markup, let's remove rendered equals false, and let's also remove loaded equals false in this case for the button, and resave our page. And again, if we take a look at the generated test.java, in this particular instance, what we now find is that we now have both of those controls being loaded and rendered in this particular case. So if we now go back to our browser and refresh our test page, here we can see that both controls now appear within the resultant HTML markup, as we can see here. And furthermore, if we were to create another session dump and look at the structure of the page, what we can now see is that the page does include an instance of both a command button and the input text control. So as you can see here, with these simple tests, the use of loaded is very absolute, in that if a control is loaded, it will be present within the component tree, and thereafter the rendered property will simply control whether the control will be present within the generated HTML markup, versus if a control is not loaded, then the render property has no effect on that control, simply because the control will not exist within the component tree. Let me now go back to Designer, where we can look at a different example taken from the lifecycle.nsf application. Within the application, you will find a page called Test Loaded and Rendered, as we can see here on the index. So I simply open up Test Loaded and Rendered. And let me also take you back to Designer, as aforementioned, and let's look at the XSP markup for that particular page. So what we've got here is a very simple X page containing a number of controls that make use of the loaded versus rendered property. And in doing so, simply emit println statements to the server console and explicitly return true to those evaluations. Now, the reason for this is that we can use this technique in order to see exactly where these properties are being evaluated during the life cycle when we have our debug phase listener activated. So let's go back to our browser application and also bring up our server console. And if we just open up the application, and one thing we must do here is turn on debug mode, of course. And let's go back to the test loaded and rendered page. Now in this case, what I'm doing is highlighting the URL and pressing the enter key. And in this particular case, what I'm doing is causing a reload of the X page itself. So in this case, what we see is that in the server console, we have the print statements for the loaded properties being invoked for each of the controls. So for the panel, the input text, and the button residing on this page, the loaded property is being activated and evaluated during the create view process, given that this is a simple GET request. And subsequently then, in the render response phase, we see that the computed rendered properties emit their print statements and of course explicitly return true during the render response phase, of course. So let's now go back to the web page, and in this case, let's do a postback of the page. When I click this submit button, it's going to cause a server-side event handler to be triggered. And if we now take a look at the server console output or debug mode, here we can now see the effect of the computed rendered property versus the loaded property in this particular case. As aforementioned in the description earlier, the loaded property will not be re-evaluated on subsequent requests against the current X page. So in this case, what we've got is a post request being acted upon the current X page that has already been loaded. So of course, in this case, we do not see any computed loaded property statements versus the computed rendered property, which aforementioned earlier in the slides will be re-executed, re-evaluated for every request against a given X page. And it was also described as being evaluated in 4 out of up to 6 phases for a simple post request, which is now in line with what we're seeing here. So for example, here we can see the computed rendered properties being evaluated during phase 2, also during phase 3, as we can see here, phase 4, and finally during the render response phase. So this is one of the main reasons why it is important to understand the difference between loaded versus rendered. You potentially, as an XPages developer, may have lots of computed rendered expressions within your XPages application. Some may be more complex than others, and many of those may be getting evaluated during postback requests and are causing extra CPU and memory usage for any given XPage request. It is also important to state the fact that the rendered property is a property that comes from the underlying Java Server Faces framework versus the loaded property, which is an XPages addition. The loaded property is one of those properties that has been introduced explicitly by XPages as an extension of the Java Server Faces framework. And in the case of the rendered property, it is not just only used to decide whether to render the HTML markup for any given control, but it is also used in order to determine whether to process any given XPages control during the processing of a component tree. That is to say that if a given control should not be rendered, then it will be excluded from the processing of that component tree. So in summary, the rendered property has a twofold purpose. Firstly, to establish whether to process a control, and secondly, whether to actually render the HTML markup for the control. So let's now go back to Designer, and I'll show you a different example that I want to explain. So if we come back into Designer, you will find the Test Advanced Lifecycle XPage. So if I open up this XPage, what you will find is that we have an XPage here containing a number of nested panel controls and a number of different buttons that execute server-side event handlers with different permutations of settings, such as partial refresh, along with immediate and disable validators, and partial refresh and execution, and so forth. So let's now take a look at the XSP markup source for this particular XPage. So on this page, you will find a number of different computed properties and events and event handlers that all basically emit println statements, and as aforementioned, use such things as partial refresh and partial execution and different permutations of those, all in an attempt to give us an overall sense of what is happening with requests that are issued against this particular XPage, based on the configuration of any particular event handler that is executed against this XPage and its corresponding component tree. The most interesting parts of this page are as follows. Note here on line 40, we do have a panel control, which is named as P1. We also have another nested panel named P2 as a child of P1. Furthermore, we also have three different computed fields. As seen here, we have computed field text1. We also have computed field text2. And we also have a third one, which sits further down the page, but is outside of both panels. So it is not a direct child of either P1 or P2. As we can see here on line 203, we have text3. Also note the fact that these three computed fields all make use of computed rendered and computed loaded properties, emitting println statements and explicitly returning true in each case. Furthermore, we then have an input text field, as we can see here on line 64, that is required. It is disabling client-side validation, and we also have a series of different buttons. Here on line 99, we have the first of the P2 buttons. And these buttons are set up with server-side event handlers that are configured differently in each case in order to demonstrate the different permutations of configuring an event handler that will interact with the XPages Request Processing Lifecycle accordingly. In all cases, again, the event handlers are running some simple server-side JavaScript in order to emit println statements, as we can see here. So let me just go to the design view. So as we can see here, the P2 panel is denoted by this blue hashed line versus the P1 panel, which is denoted by this green hashed line. And notice the fact that inside the P2 panel, the buttons that I'm describing are direct children of the P2 panel. So we have a group here of buttons that all indicate in their titles that they belong to the P2 panel, versus these three buttons that are direct children of the P1 panel, and again denoted in their titles as children of the P1 panel. We then also have a series of buttons that sit outside of the P1 and P2 panels. They are not direct children of either of those two panels, as we can see here at the bottom of the page. And we'll come back to those in a few moments. So coming back to the buttons that are within the P2 panel, we can see that there are different descriptions on each of their titles. So in this case, P2 STD denotes the fact that this button is a child of the P2 panel, and it's a standard event handler. There is no special configuration set on the event handler. It's a simple event handler that will submit and do a full refresh of the page. The next button, P2 Standard Immediate, simply means that it is a standard event handler with the immediate property set to true. And on the same token, this P2 Standard Disable Validators simply has the Disable Validators property set to true. And within the next row of buttons, the P2 PR denotes that partial refresh is set on this button, and the target for that partial refresh is indeed its direct parent, the P2 panel. And the same applies for the other two P2 buttons that we see listed on the same row. And finally, in the last row of buttons within the P2 panel, the P2 PRE denotes that this button has partial refresh and partial execution configured. And again, the target is the P2 panel for the partial refresh and partial execution. And the same applies for the P1 set of buttons that we see listed at the bottom of the P1 panel. This denotes that this button has partial refresh and partial execution configured, and its target is the P1 panel. And finally, for the set of buttons that we see defined at the bottom of the page that are not direct children of either P1 or P2 panels, and for this particular button, we can see that partial execution is configured and it will do a full refresh against the P2 panel. Likewise, this next button, again, will partial execute and partial refresh the P2 panel. And this one will do a full execution and a partial refresh of the P2 panel, versus this last set of three buttons, which have no IDs set, which means that effectively they will partial execute and partial refresh per their own configurations using no target ID. But the important aspect to note about the bottom set of buttons is the fact that they exist outside of the two P1, P2 panels. So let's now go to our browser and use our debug mode to analyze the behavior of this particular XPage. So the first thing we need to do is come back to our XPage application, lifecycle.nsf, and turn on debug mode again. Let me just bring up the browser and server together, and then we can open up our Test Advanced Lifecycle XPage. And let me also just maximize the browser. So as you can see here, at runtime we have our three computed fields showing the system time milliseconds. And also note the way that they are children of the P1 panel, the P2 panel, and of course the third one sits outside of those two panels. And also note that if I were to click on P2 standard disable validators, in this case, Notice how the three computed fields are changing their values. So those three computed fields have a computed value, which is simply a runtime server-side JavaScript expression that is showing the current system time milliseconds. So I'll now just reduce my browser so we can see what's happening on the server console as well. Now let me just repeat the same button click for P2 standard disable validators. And let's take a fresh look at what has happened on the server console in relation to the request processing lifecycle. So as we can see here, the request has come into the server and we restore the view, given that it is a post request, apply request values and so forth through the different phases of the lifecycle. But what's interesting to note is the presence of our computed rendered expressions being evaluated within 4 of the 6 phases in this case. And for this particular use case, the P2 standard disable validators button is submitting a post request to the server, but it is also performing a full page refresh. There's no partial refresh being used here or no partial execution. Furthermore, this particular example is using the disable validators property on the event handler, which in this case is disabling the required clause that would otherwise be invoked on the input field. So indeed we could go back and perform the same operation but use some of the other P2 standard variations. So for example, if I were to click on P2 standard, it will of course cause an invocation of the required clause on the input field. Or if I were to click on P2 standard immediate, this would of course again cause a full refresh, but because we're using the immediate property, it would avoid any processing of the validators on the input field. So if, for example, I click on P2 standard without supplying a value for the input field, as you can see here, the validator has been invoked. And within the server console, here we can see that the request started, restored the view, applied the request values, and subsequently processed validations, caused an invocation of all the validators on the page, and in turn the input field required clause failed, causing the failover into the render response phase. Versus our second example, P2 standard immediate, what I could do here is click on this particular button, and in this case, the process validations phase, as we can see here, we restore view, but the process validations phase is not even executed. We avoid going into phases 3, 4, and 5 in this particular case. But the interesting point to note is the fact that in all cases, regardless of which variation of the event handler configuration we use, the computed rendered properties still are executed in multiple phases for each of those types of requests. And also note the fact that given that we are doing a full page refresh, this means that there is an entire execution of the component tree on the server side. Hence the reason that we see multiple computed renders for each of the different areas that we have on the page. So for example, the text1 computed field, as we know, sits inside the P1 panel. The text2 computed field, of course, is inside the P2 panel. And then the third text3 computed field sits outside of those two panels. So we're using those computed render properties to give us insight into which parts of the component tree are being executed for our requests. So let's now do something slightly different. Let's go back to our example, and in this particular case, let's use the middle set of buttons, the P2 variants, which are using partial refresh, of course. So let's perform the same operations. So for example, let me just go ahead and click on P2 PR disable validators. And in this case, as aforementioned, the target area of the partial refresh is indeed the P2 area. And I can also just confirm that to you. If we go back into Designer and look at the configuration for this event handler, as you can see here, In the server options, we have our partial update area as the P2 panel, and we're also using the disable validators property in this case. But again, as aforementioned, regardless of the fact that we use immediate or disable validators or not, we will have execution of the computed renders within the different areas of the component tree. But in this particular case, we're also using then partial refresh against the P2 area. So let's just go back then to our server and application. So in this particular case, having already executed the event handler for the P2 partial refresh disable validators button, here we can see that the invocation of that request has come into the server, restored the view, and so forth. But what's interesting in this particular case is that within each of the lifecycle phases, as we can see here inside phase 2, the apply request values phase, the computed fields that are contained within the other parts of the component tree are still being executed. And that is true for phases 2, 3, 4, but not for the last phase, which is the render response phase. So notice in this particular instance, we only have the text2 computed field being executed during the render response phase. And this is in line with the configuration of the event handler. The target for the partial refresh is the P2 area. The computed field text2 sits within that P2 panel. Hence, in this particular case, during the render response phase, only that part of the component tree, that is the P2 area and its children, are being executed. And then the corresponding HTML markup is being sent back to the requesting browser. And once again, I can't confirm that for you back inside the browser. If we come back into the browser, and let me just open up the developer tools and look at the network traffic. So in this case, when I click on P2 PR disable validators, in this case, what we will see is the P2 PR request being issued, and we will then see the network traffic and response that we get back from the server here inside the developer tools. So here I click on P2 PR, disable validators, and in this case, as we can see here, we have issued a post request. And when I take a look at the post request and the response information, what we see indeed is that we are issuing a AJAX request using the XML HTTP request object. The target of our partial refresh invocation is indeed, as we see here, the AJAX ID P2, the P2 panel. And then if we take a look at our response, what we see is that we only get back the relevant HTML markup for the P2 area. So as you can see here, we have the containing P2 panel, which translates as a div HTML element, as we can see here, along with its child HTML elements. And let me also show you something else of relevance within this area. If we go back to Designer, and if I go to the application properties, and if we take a look at the persistence options under the XSP properties, here we can see that there is an option that has been available since 8.5.1, whereby we can configure whether to evaluate the entire page on partial refresh. Up until 8.5.1, the default for this particular behavior was to evaluate the entire page. Whereas in 8.5.1, this optimization was introduced in order to reduce the amount of processing against the component tree within the render response phase. So in this particular example, it is using its default value of being unchecked. But let's say, for example, we now check this particular option, which in turn writes this particular property into the XSP properties file, as you can see here, XSP AJAX render whole tree. And if we then go back to our application and server console, and let's perform the same operation. So of course, in this case, we need to refresh the app, reset debug mode, Again, just let me refresh the XPage itself. And if we now choose to select P2 PR Disable Validators, what you can see in this particular case is that even though we're issuing partial refresh request, notice the fact that the render response phase is now executing the entire component tree. The other computed fields within the other parts of the component tree are also being invoked. So the text1, text2, and text3 computed fields are all being executed. And of course, if we go into the browser and again use our developer tools and issue the same request, we are still getting back just the HTML markup for the P2 panel. But of course, as we have just learned here, back on the server side, the entire component tree has just been executed. Now, the reason that that particular property is exposed inside the application properties is to allow any pre-851 applications to still behave the way that they may have done prior to 851. In that, during the render response phase, there may be server-side logic, such as server-side JavaScript or custom Java, that is dependent upon the value of some other control sitting outside the target partial refresh area. And that other dependent control is having its value reset during the render response phase. But it is strongly encouraged not to be resetting values during the render response phase. Now let me just go back and reset that property inside our application properties before we continue. And in the next example, what I want to do is look at the third set of buttons within the P2 panel. So that's the P2 PRE set of buttons that we see listed here. And in this particular case, if I just show you the server options for P2 PRE Disable Validators button, as we can see here, it is using partial refresh to partial refresh the P2 panel. But furthermore, it is also using partial execution mode. And here inside Domino Designer 9.0, there is now a button which exposes the select element dialog, which allows you to pick the target area. So having checked the checkbox for set partial execution mode, I have also selected the P2 area. So here we can see that my partial refresh area is P2, but my partial execution area is also P2. And I should also say that if you're using a version of Domino Designer prior to 9.0, you can also find the property for setting the partial execution ID directly on the event handler for the button itself. So for example, if I select the event handler here on line 167, as you can see here, the event handler tag. And then if we look at the all properties for that particular tag, what you can see here is that in amongst the different properties, we have an execute ID property. And in this particular case, I've just set the string P2. And the execute mode, of course, by checking the checkbox, will set partial as that option. As you can see there, inside the XSP markup, those properties have been set accordingly. As we can see here, we have our refresh mode is partial, refresh ID P2, execution mode partial, and execution ID P2. Once again, having made changes to the application, let me just come back and refresh the application. And once again, let's use our server console and our P2 buttons. So in this case, I'm going to click on P2 PRE Disable Validators. And in this particular case, now we see the effects of using partial execution to complement partial refresh. Notice that for this particular request, the request has come in, restored to view, we've gone into the apply request values phase, and right away we are only executing the P2 target area of the partial execution, which means that just the text2 computed field is being invoked in this particular case. And that holds true for the other phases. So for example, here we see process validations, only executing computed field text2, update model values, only executing computed field text2, And finally, during the render response phase, our partial refresh target being the P2 area, meaning that we only then execute the P2 area and send back the relevant HTML markup for that area. So once again, just to give you a comparison, if I just come back to the application and using the older approach whereby I click on P2 standard, disable validators, and just to remind you, of course, here you can see all three computed fields being executed in each case, versus using partial refresh. Again, all three computed fields are all parts of the component tree being executed within each phase. Apart from the last phase, given that we're using partial refresh, just the target area in this particular case, versus our use of partial refresh and partial execution in the last button, which results in a minimized amount of execution. As we can see here, just the text2 area in each of those different phases. And of course, during render response, just that target area again. Now, also let me show you the other buttons then that sit outside of the nested panels. We have the P2 partial execute and full refresh button. Now let me just go to Designer and show you the event handler in this particular case, because this is where things can get a little bit interesting if you're not careful when using partial execution and partial refresh and so forth. Notice that the event handler for this particular button will print a console output statement, but in doing so it is getting the input text control, input text 1, and getting its value and concatenating that with the print statement. So in this particular case, when we click on the button, we would expect to find that we get the value of input text 1 and so forth, and see the console output accordingly. But furthermore, take a look at the configuration for this particular button. Notice that we are using partial execution. In this particular case, we're not using partial update, but we are using partial execution, and that's something important to note. You can use partial execution and or partial refresh together. And in this particular case, as you can see here, what we're expecting to do is partially execute a target area of the component tree, but effectively have a full refresh of the page. But that partial execution is targeting just the P2 panel in this particular case. And do remember that this particular button and event handler do sit outside the P2 area. Now let's go to our server console and our browser, and let's put a value into the input field. So in this case, here we have hello world inside the input text. And what we're going to do now is click on this P2 partial execute full refresh button. So I click on the button, and the request has gone through to the server and being processed. So in this particular case, notice that we restore the view, apply request values, and so forth. But notice the fact that given that we're targeting the P2 area for the partial execution, we do see the computed field within the P2 area being executed within each of the phases. But notice that during the invoke application phase, the event handler of the button has been ignored. And then, given that we're doing a full refresh, we're not using partial refresh, during render response, of course, we do see the entire component tree being executed for rendering back to the requesting browser. So the question here is, why did the event handler be ignored during invoke application phase? Well, the reason is because our target area for the partial execution is the P2 area. And if you think of it like this, here we have the P2 area denoted by the blue hash line, of course. And our button that we have just executed, along with its event handler, sits outside of this area. It is not a child of the P2 area. Hence, when the component tree has been executed, given that the event handler for the incoming request sits outside of that partial execution area, it is totally ignored. And we can also see the same type of behavior if we take a look at the next button, which alludes to the fact that it is using partial execution and partial refresh. And again, it is targeting the P2 area. If I click on that particular button, we also see the same behavior. The event handler for that particular button is being ignored. And again, we see how we're using partial execution to minimize the amount of execution, and partial refresh, of course, to minimize the amount of rendering processing during render response phase. So if we finally just look at the last particular button in that particular case, here we have P2 full execute with partial refresh. So if I click on full execute partial refresh, now we see the event handler being invoked. So in this particular case, here we see the event handler causing the server console output and of course getting the value of the input text 1 field, given that we're performing a full execution of the componentry as we see here. So what's important to note here is the fact that you can broaden or narrow the scope of execution. So when you want to complement partial refresh and partial execution together, you should consider the magnitude of the execution scope. Do you need to broaden or narrow the execution scope of partial execution in comparison to the partial refresh area, and vice versa? And as you can see here, this is a very powerful mechanism whereby you as the XPages developer have full control over the magnitude of your event handler, both in terms of server-side execution and the resultant HTML markup that gets sent back to the requesting browser. And furthermore, when you pair your knowledge of using partial execution and partial refresh together with such things as the immediate property and the disabled validators property, you are then applying the most influence over the behavior of your application in terms of its use of memory and CPU relative to the processing of the XPages Request Processing Lifecycle. And therefore, it is you that is having the most influence over the efficiency of the processing of any given request. In this final section of video 4 from Series 1, I now want to demonstrate an application that brings together everything that we've learnt about the XPages Request Processing Lifecycle into a couple of worked use cases that we can then use the XPages toolbox to profile. And from those profiling results, we are able to then measure and appreciate how having a good understanding and applying that understanding to an application will have a beneficial impact upon the performance and scalability of that application. So here inside Designer, I have taken the liberty of opening up two applications, the Greenwell Help Desk number 1 and the Greenwell Help Desk number 3. And from each of those two applications, I have opened up one custom control of interest. It's the all docs, all tab custom control. And in both cases, as you can see here, visually the two look more or less identical within Designer. But the points of interest that I want to highlight with you today involve two computed fields and a link with a server-side event handler. So as we can see here, we have a CF abstract computed field, but we also have a second one which displays a static value. And then of course we have this track link. And if I compare that to the second custom control, what we see is that we simply have one computed field and of course the same link with an event handler. In terms of ownership, the first custom control we see listed here on the left comes from the Greenwell Help Desk 1 application. And the one on the right side comes from the Greenwell Help Desk 3 application. So let me now go to the browser. And as you can see here, I've already opened up the two Greenwell Help Desk applications, and I've also got the XPages toolbox opened. And what I'm going to do is use the XPages toolbox to profile two different use cases within each of those two applications. And then I'll explain the profiling results in relation to the differences between the two different custom controls within each application. So firstly, what I'm going to do is come into Greenwell Help Desk 1, and I've gone here to the All Documents X page, which shows the All Docs by All Tab custom control that we're interested in. So the first thing I want to do on this particular X page is expand out the number of rows to 500. Now, I do understand this is not a typical use case for a web interface, but it has been used here simply to exaggerate some of the effects of the XPages Request Processing Lifecycle in relation to how this particular custom control has been configured. So here I just click on 500 in order to expand out the number of rows. And the two different use cases that I want to elaborate on today involve clicking on this track link that we see here. And in doing so, we then invoke a server-side event handler that will run some server-side JavaScript code. So the notion here is that we can track a particular entry within the view, where a direct analogy would be like a Facebook like, for example. And the second use case will then be simply a case of paging through the dataset. So what we will do is profile the action of paging from page 1 to 2 and so forth. And we'll repeat those two same use cases within the Greenwell Help Desk 3 application, of course. So firstly, let's profile the paging example. So if I come back to the toolbox, and I'm just going to start the wall timer, and then come back to the Help Desk application, and now I click on Go to Next Page. So currently here we're sitting waiting on the pager to take us across to page 2. And here we can see that it has now completed, and we're on page 2. So let's go back to our toolbox and stop the profiler. And I'll just reset the profiler so that it's ready for the next profile snapshot. But let's take a look now at this particular use case. We've just paged from page 1 to page 2 in Greenwell Help Desk 1. And immediately I can see here that we have got a total response time of just over 10 seconds, which is absolutely unacceptable for such a trivial action. So let me just collapse the results, and then we can drill down into the information to gain a deeper understanding of where the time is being spent and so forth. So first off, what I've done here is expand out the lifecycle phases. And what we can see here is that we are triggering a post request, given that we can see all 6 phases being involved. And furthermore, if we then look at the execution points sitting within each of those phases, I just expand everything, we can start to see that within certain phases we have what appears to be multiple invocations of certain fragments of code, as we can see here, 500. And furthermore, we can also see that some of the most costly operations appear to be repeated within different phases of the lifecycle. So for example, here we have a reference to var on ID2 equals view entry, and so on, being executed 500 times with a specific time of just under half a second. And then we also have this var on ID1 equals view entry, again 500 invocations, taking just over 1 second. And I also seem to be getting the same type of invocations within the next phase of the lifecycle. As we can see here inside the update model values, we have the same reference being picked up, and again consuming more time within the request processing lifecycle. And again, if I just move down through the results, the same holds true for the apply request values phase. and also inside the render response phase. Now, before going back to Designer to look at the code, let's carry out the same use case within the other Greenwell Help Desk 3 application. So once again, I just go over to the Greenwell Help Desk application and let me expand out the number of rows to 500 and come back to the toolbox. We reset our profiler and start the wall timer again. Come back to the Greenwell Help Desk and click on Next. So immediately I can see that it was much quicker. So coming back into the toolbox, I will stop the profiler. And in this particular instance, as we can see, the total time is now just shy of half a second. So there is a significant difference between the two applications. One taking over 10 seconds to page, the other taking less than half a second. Once again, just let me collapse everything and then we can drill into the information. And in this particular case, I can see that there are only 3 phases of the life cycle involved, as opposed to the 6 phases that we see for the previous request. So in the first request, as we see, just over 10 seconds, involving 6 phases of the life cycle, versus our second request, taking just under half a second, and only involving 3 phases of the life cycle. Furthermore, if I just expand all the information, if we look inside the execution points within the different phases, we can see that inside Restore View and Apply Request Values, there is negligible amount of time spent in any particular execution point. All of the hard work is being done inside the render response phase. And in this particular case, even though we have multiple invocations of some of the same JavaScript expressions coming from the JavaScript cache, none of those invocations are using up a significant amount of time. Therefore, confirming to us that this is a particularly well-coded version of that same custom control. And once again, before we go back to Designer to look at those 2 custom controls in more detail, let's also carry out our second use case where we click on the track button. Once again, just let me reset the profiler and start the wall timer. And in this particular case, what I'm going to do is expand a row, and I'll also use my server console, because when I click on track, there will be some server console output confirming to me that the server-side action has indeed been invoked. So here I go and click on track. And again, I'm currently sitting waiting on the action to perform, and lo and behold, it is just completed. So I've clicked on track, and here I can see this track console output confirming to me that the action took place. So let me go back to the toolbox and stop the profiler. And for this particular tracking action, as you can see here, it took almost 8 seconds to invoke that particular server-side event handler. And if we look at the execution points for the request, here we can see, once again, multiple invocations of what appears to be the same JavaScript expressions occurring multiple times within the different lifecycle phases. So this profiling snapshot certainly confirms to us that there is a high level of redundancy within the code of this particular application. So let's now go ahead and perform the same use case within Greenwell Help Desk 3. Once again, I reset the profiler, start the wall timer, and we come over to Greenwell Help Desk 3. And let me just expand a row. Once again, let's view our server console so we have visual confirmation of the track event occurring. So here I click on track, and instantaneously, as soon as I click, it's confirmed to me on the server console that the tracking event has occurred. And just to confirm those findings, when we come back to the toolbox and I stop the profiler, in this case, here we see that the exact same event took less than 2/100ths of a second. And when we look at the snapshot, again, here we can see a reduced number of lifecycle phases involved. We simply have 3 in this instance. And in terms of multiple invocations, in the previous snapshot, we've seen that there were, in some cases, 500 invocations, as seen here, versus in our new snapshot, we only ever seem to execute 1 or 2 particular execution points. And the times, as we can see here, are negligible. So, in summary, just let me then collapse all of the information for our 4 different use cases, 2 from each application. And as we can see here, for Greenwell Help Desk 1, the paging action took over 10 seconds. The tracking event took less than 8 seconds. Versus Greenwell Help Desk 3 application, the paging action took less than half a second, and the tracking event took less than 2/100ths of a second. So these are radical differences exposed by 2 versions of pretty much the same application. And I can now confirm to you that these differences are simply exposed by careful application of an understanding of the XPages Request Processing Lifecycle, whereby careful use of computed rendered, partial execution and partial refresh has been configured within each of those 2 custom controls. So let's now go back to Designer and look at the key differences. So in the case of All Docs All Tab from the first Greenwell Help Desk application, if we look at the source markup, we have 2 computed fields being used to display an abstract. And for each of those 2 custom controls, there is use made of a computed rendered property, which is performing a fairly intensive operation upon the Notes Domino backend. And as we can see here, we have the reference that has been used back in the profiling results coming from the server-side JavaScript cache, var on ID 1, and so forth. But like I say, it's a fairly intense operation to be carrying out inside a computed rendered property. Given what we know about the computed rendered property, in that it will be re-executed in up to 4 out of 6 phases for any given post-back operation. And as I've just explained, for the second abstract computed field, again, it's doing nothing more than simply showing a static value if an abstract doesn't exist. But once again, it's using a computed rendered property, performing another fairly intensive operation, as we can see here. And again, notice the reference that we see back inside the profiling results, var on ID 2. So you might actually be saying to yourself that you would never code something like this, in that you would use 2 computed fields to show a very simple abstract field, and you would never go off and get a document in a view in order to get an item value string and so forth. But what I can say is that this is based upon multiple customer examples that I have had the pleasure of reworking and correcting. And if we take a look at the second All Docs All Tab, if we then look at the computed field for the abstract, here we see there is only now 1 computed field. And in this case, the computed field is not making use of any computed rendered. It's simply setting its value based on the column value for the abstract. So the key difference here is that instead of asking the XPage to perform all this heavy lifting to go off and get a document within the current row and get an item value and so forth, what is happening here then is that the backend view has been given a new column and the abstract data is then populated into that backend view. So we're making better use of the backend view resource. And in a sense, we are decoupling the XPage from having to do some heavy lifting in terms of back-end view, data retrieval, and simply leaving the XPage to be more of a presentation layer in this particular case. And then if we come back to the first all docs all tab custom control and look at the two different links. So for the tracking link, as you can see, it's a very, very simple println statement. So there is no heavy lifting occurring within the actual event handler itself. But yet and all, inside the first Greenwell help desk application, we did see that this particular link did take in the order of almost 8 seconds to execute this very simple println statement. Now that is a consequence of the event handler not using partial refresh, as we can see here, not using partial execution, and also not using the immediate property, given that it would be applicable in this particular case. So essentially what is happening here, when we click on the link, the event handler is causing a full page refresh, which subsequently then causes the two computed fields that we see above to have their computed rendered properties re-executed through the different phases of the life cycle and so forth, along with everything else on the component tree at that particular point in time. Hence the reason that we were seeing almost 8 seconds being used to process that particular event handler. If we then compare that with Greenwell Help Desk 3, if we take a look at this particular link, as we can see here, it's performing the exact same operation, a very simple println statement on the server console. But in this case, it makes better use of the XPages Request Processing Lifecycle. And in doing so, it is using partial refresh, but also partial execution. And it is isolating the execution within the component tree to this link itself. As we can see here, we have partial refresh for the link itself, but also partial execution for the link itself. And just as an added bonus, as we can see, it also makes use of the immediate property to avoid processing phases 3, 4, and 5. And what I can also confirm to you is that in terms of the two pagers that we profiled as well, the reason that the first Greenwell Help Desk application was performing so badly when paging was simply a consequence again of the multiple invocation of the computer render properties and so forth, versus in this second case, because we have minimized the amount of redundancy, and again, in this case, this particular computed field has no computed rendered property and so forth, the paging then occurs much quicker. And in essence, the results that have been achieved are simply a consequence of careful application of using the XPages Request Processing Lifecycle versus a case where there was no consideration. So just to close up on this particular example, what I would like to do is just reiterate the differences that we see here. Once again, as aforementioned, in Greenwell Help Desk 1, we see two operations that took over 10 seconds and almost 8 seconds in each case, versus in the optimized version, with careful use being made of the XPages Request Processing Lifecycle, we've seen results that were minimized to less than half a second and under 2/100ths of a second for the exact same operations. So I do hope that you have enjoyed this first XPages Masterclass video series and have found it particularly useful and can see opportunities now within your own XPages applications to make better use of the XPages Request Processing Lifecycle. Thank you. This is the end of video 4, the last video from the first series.